So what happens, or according to our new modern physics, metal consists of a lattice of fixed positively charged ions in which billions of free electrons are moving randomly at speed uh, which, as per kinetic theory of gases, is given by this. You must have studied in KTG that this is 3 kT divided by m. This is called root mean square velocity, VRMS, velocity of the electrons in the metals, free electrons. So this is velocity, or better, random velocity of free electrons in solids, or in metals, or I'll say in lattice, right? So what is there? There are lots of positively charged ions in this solid lattice which are fixed. So these are positively charged ion. These are not going to move. These are fixed. All are positively charged. And if there is an electron, the free electron is that electron which is somewhere over here, right? So these electrons, they move randomly, and they, for example, if there is a positive charge here, there can be another electron also in the same region. So they occur, or they experience different types of forces on that, or collisions. So some collisions will be there, or to avoid collisions. So you can see here the movement of an electron, of a free electron, is random. That is, they are moving in random direction or in all directions, not in one direction. So this flow is random. So this flow, that is random flow, is not equal to current, because current is the flow in a given direction which has a similar, or which has a one unique direction, right? And meanwhile, this value of VRMS comes out to be 10 to the power 5 meters per second, which is a very huge value. That means these electrons are moving very fast, and at the same time they are moving very fast in random directions. So that is not current for us, right? So in absence of any electric field due to this random motion, the number of electrons crossing from, say, suppose this is the boundary. Suppose this is the boundary of the metal, or one section of the metal. Now, if there is no electric field, and these negatively charged electrons, which you can see here, are moving in random motion, the number of electrons crossing from, say, one end to another end, say from here to here, if I want to find out number of electrons which have crossed this, so that will be very, very less, right? So this means, so the net current through the cross section is almost zero, right? So motion of charge is possible by motion of electrons or a current carrier. So that is there, motion is there, but this motion is random motion. So I can say net current is equals to zero. Okay, so they remain in their own, as you can see, boundaries. They do not cross that boundary, and that's why there is no use of that. We are not getting any current due to that. Now what happens? The velocities of charged particles, which we see here, that is in this conductor, the electron which was moving. So it has the velocity with which it moves, that is called thermal velocity, because it is related to heat. So we are not heating it, but the metals in its natural state is very high, is at very high temperature if we consider the reference temperature to be the critical temperature, that is the absolute zero temperature. So if we consider that as our reference, then from that we already know that it is, if it is 23 degrees Celsius, that is around 300 Kelvin. So from absolute zero, it is 300 units more. So that is a huge temperature gap. And for metals, that is sufficient to excite their electrons to leave the metal atom and come into the free or the space in the solid lattice, and that's how we get free electrons. Now all electrons in the atoms are not capable of motion. Only a few which have little higher level of energy level than their orbit and are capable of moving around. These electrons are called free electrons. These free electrons are in very large quantity in metals, and due to temperature and thermal energy, they have a thermal velocity which is of the range 10 to the power 5 meters per second, which we have seen earlier. This velocity is in all directions and of magnitudes varying from 0 to maximum. It's not like that all the free electrons are moving with same velocity of 10 to the power 5 in random direction. So once they collide, they're due to collision or due to repulsion or due to attraction, there all these things will happen. Attraction between the positively charged ion and the electron, repulsion between electron and electron, collision between electron and electron, and positively charged ion. So all these things happen, and due to that, the speed and even the velocity keeps on changing with time. So this change can be from 0 to maximum, and due to large number of electrons, because there are huge number of electrons, we assume that vector sum of thermal velocities at any instant is 0, right? So we have this thermal velocity, which is due to, or we can say this is random velocities of free electrons, right? And we say that their sum, their vector sum of all such thermal velocities, let us say we represent it by ut. So all such ut, that is thermal velocity, is assumed to be 0. So vector sum of all such ut is assumed to be 0. Why this assumption is safe? Because there is large number of such moving electrons. So that's why I assume that, because all of them, suppose one is moving in this direction, there are high chances that there will be someone moving in this direction with the same velocity. So that will cancel each other. Same way, if some electron is moving in this direction, another electron is moving in this direction, so they will cancel. There is high possibility of things like this. So that's why we say that the average thermal velocity as well as the total thermal velocity is equals to 0. That is, suppose you have velocities u1 plus u2 plus u3, so on till un. If we know the total number of electrons, we say that this is equals to 0. So that is the thermal velocity. And what did we understand about this? That its mean is equals to 0, or its vector sum is equals to 0. Another term which we should know is called mean free path. Now, what is this mean free path? The fast moving electrons keep striking other atoms or ions in the conductor because they are moving in random direction, so they'll strike or collide with other atoms or ions in the conductor. Now they are reflected and move in other direction, and they keep moving till they strike another ion or atom again, right? So suppose if this is that moving electron, so this is moving right now, so it will keep on moving in this straight direction till they strike some atom or ion. Now, suppose this is that thing to which it strikes, then what will happen? Due to this collision, the path or the direction of this electron will now change. So from here, it may start moving in this direction. And again, there is a chance that it will collide with something else. And again, due to that, it may move in some other direction. Correct? Again, if it collides, it may come to some other direction. So when it is between two collisions, the path is always a straight line, right? So path between two collisions is a straight line. It's not a curve. The path between two consecutive collisions is called free path. Path between two collisions is a straight line, and this is called free path, right? It's not mean free path yet. This path is called free path. That means this, all these straight lines which we see here, right? So this is a straight line, this is a free path, this is also a free path, this is also a free path, this is also a free path. So all these highlighted paths are actually free paths. They are simple straight line. The average length of these free path is called mean free path. Right? What is mean free path? Mean free path is average. Mean means what? Average. So average length of free paths is called mean free path. So for example, if suppose there are 4 free paths which we are saying here, and suppose their length are some A, B, C, D. So the mean free path will be A plus B plus C plus D divided by 2. So that is average length of free path, and that is what mean free path is. Next term. So our next term is relaxation time. Now what is relaxation time? The time to travel mean free path is called relaxation period or relaxation time. Time to travel mean free path, that is called relaxation time or relaxation period. And how do we represent it? We represent it using this symbol tau, which we use for torque as well. So suppose for each collision, time taken is t1, t2, t3 till tn. Then the relaxation time will be total time divided by the number of collisions. right? So this tau is equals to T1 plus T2 plus T3 on till Tn divided by n. That is mean free paths, where what is T1, T2, T3 and all, what are these? These are the time periods for collisions. Time periods for collisions. That means, suppose in this, in the same figure, suppose the time taken here is uh, 2 milliseconds, or it will be very less, but suppose we are taking 2 units. This is 3 units, this is 4 unit, and this is also 2 unit. So in that above example, it will be 2 plus 3 plus 4 plus 2 divided by 4. These many seconds or whatever units we have. So that is 5 plus 4, 9 plus 2, 11 by 4. That is 2.75 units. So same thing for mean free path as well as for relaxation time, we'll have the same formula, I mean same process. Next very important term, and for which we also have few derivations, that is called drift velocity. So we saw that due to this thermal velocity, there is no net current, or it does not move in a single or given direction. It keeps on moving in random directions. So if something keeps moving in random direction, that's not current. So from where this current comes into picture? And we from our day-to-day life observe that a wire on its own does not contain current. When current is established in wire, when the wire is actually connected in a circuit containing a battery, then only that metal or that wire or that conductor will start conducting electricity. Okay, now so now what we have to do is we have to find out the ways to calculate this drift velocity and to understand what is this drift velocity. Now when electric field is applied across a conductor, the free electrons will obviously, what we have seen earlier is that there was this conductor. In this conductor there were these electrons as well as the positively charged ions. The positively charged ions are not moving, that we understood, but these electrons which are there, they are moving in random directions, due to which there was no current. Now, if we want them to move in a single or given direction, the free electrons must be uh, put in an electric field or in an external electric field. So we establish an electric field. Suppose this is the direction of electric field. Somehow we are able to achieve this. That is the electric field. Now, if electric field is moving in this direction, that is from left to right, electrons, which we see here, are negatively charged. So what will happen to these electrons? Now they will experience a force in this direction. This is the direction of force on each electron, right? And as I said, this is just the direction of force. Now, before this electric field or before this force, due to this random motion, this may be going like this. This means the electron may be moving like this. But what will happen now due to this electric field E? Now what will happen? Now it will experience a force. What will be that force? That force will be some force. Suppose this force, and that is equals to EE. And its direction, as you can see here, that is in the opposite direction of the electric field. And due to that, this charge which was supposed to reach here will not reach here. It will experience a force in this direction, so obviously an acceleration in this direction. So instead of going like this, it will actually come somewhere over here. So what we see here is the electron has moved in this direction. Correct? So instead of coming to this point, it has moved to this point. So this is the drift in motion of electron. So it was going like this, but due to air, you may go like this. So this is nothing but drift. You drift from your original path. Drift is nothing but deviation from original path. And what we see here, that it's not just one electron, there are so many electrons. So every electron will suffer this drift in its normal motion, and all the drifts will be in the same direction. All the drift will be in the same direction. So they all, as you can see now in this figure, they all are drifting in the same direction. And then again, if they collide and move to somewhere else, again this electric field is still there, so they'll keep on drifting towards one direction. This velocity with which an electron drifts or electron deviates from its original path is called drift velocity. Right? The velocity to this drift is called drift velocity Vd. That's how we are going to represent it. Now during the drift, they maintain their thermal velocity as well. So that means it's not like now they'll start moving, all will start moving like this. No, it is just for very small time that they moved in that direction. Then again, there will be collisions. So again, suppose they drifted from here to here earlier. This was our D1, suppose drift 1. Then again, what is next? Next is collision. And now again, due to collision, electric field is still there. So instead of moving here, it may come here. That is again nothing but drift. That is drift 2. So like this, it will always, the net motion of this free electron will be always towards one direction or drifted towards one direction. And the velocity with which it happens, that is called drift velocity. Right? So there is a velocity, relation between this drift velocity and the electric field which we are applying. So on positive charge, as we have seen, the diagram we have already seen that if there is an electron moving, then it will experience a force in this direction, and that force will be equals to EE. Now, suppose there are n electrons having initial speed u1, u2, un as their time of travel free path, and let that be t1, t2, and tn. So we have u1, u2, u3 till un. Let this be their initial speed, and obviously initial speed is nothing but initial thermal speed. So let this be their initial speed. Next is T1, T2, T3. This is their relaxation time. So it is time to travel free path. Individual free path time. Right? So, and there is an acceleration. Let that acceleration be always, I mean, that will be anyways equal for all. So let that be equals to A. So what do we have now? We have V1 is equals to U1 plus AT. Same way V2 is equals to U2 plus AT2. And ultimately Vn will be equals to Un plus Atn. So drift velocity is average velocity of these velocities. This is the final velocity. It was moving like this. Due to this electric field, there is a force in this direction. There is an electric field in this direction. So due to that, it actually drifted to here. So this is your drift velocity of one electron, right? Not all, not of all. Now the drift velocity Vd is average of the velocities of charged particles. So the drift velocity is average of these velocities. Drift velocity is average of these velocities of charged particles. Mostly here, as you can see, will be are electrons mostly. So average, right? So that means what is Vd? Vd is V1 plus V2 plus V3 so on till Vn all divided by n. And what is V1, V2, V3? This is U1 plus AT1 plus U2 plus AT2 plus U3 plus AT3 so on till UN plus ATN. And this all to be divided by n in order to get its average. So that is our average. Now in this average we have two things. We have this group, that is U1, U2, U3, that is the initial thermal velocity. So that is anyways going to be 0. That is 1 by n U1 plus U2 plus UN. So that is sum of all thermal velocities. And then plus half. So in this, I think A will be common. So I can take A outside, and inside I have T1 plus T2 plus T3 so on till Tn. Right? So now this we know that this is 0, U1 plus U2 till UN is 0. And what about this? Sorry, this is not half, right? It is average. So average means divide by number of terms. So 1 by n. Right, so in this I can take this A outside, and yeah, that's already taken, A by n, and the sum of these relaxation time. So what is this now? This is A by n, and sum of those individual times. So I can say this is A tau. This is our Vd or drift velocity, that is equals to A into tau. So what is Vd? Vd is A into tau. Correct. Now what is A? A is acceleration, that is force divided by mass. So what is force? E E, that is electric field in sorry, yeah, electric field into E, tau divided by AE by m, where EE is the force and m is the mass of electron. So now substituting it in again, VD. So what is VD now? VD is EE by m into tau, right? So that is, and now if you consider it with 0 plus AT, so we can say that V is equals to, since I mean still alpha will be equals to EE by m, right? So that means A is equals to acceleration is equals to E divided by m. So that's what is relation between velocity, that is drift velocity, and what else? Electric field. So this is important. This is a relation between drift velocity and electric field. And where do we see this? Here. Drift velocity. Okay, anyways, you can already see here that what all terms we have here. We have electric field, that is the external electric field, and the internal drift velocity, and that is how they are related. Next, we have to study the relation between drift velocity and current. So let's study that, that is drift velocity and current. So based on what we have already done, we'll move forward. So few things we have to see here, that is drift velocity comes into picture only if there is an electric supply. So suppose this is the conductor having a unique cross section, although it is not looking like unique here. And this conductor section is connected to a battery having potential difference of V, right? So that means what? This is positive, so this will be positive, this will be negative, and electric field will be set up, which will be in this direction. Now let the length of this piece of wire or conductor be L, right? And let this cross section be A, let this cross section be B, and again electrons will leave the negative terminal and will come here like this, but protons, or sorry, the positive charge looks like moving in this direction. So we say that this is the direction of current. So few things we have to suppose here, that is say n, where n is number of electrons per unit volume, that is nothing but electron density. Then we have A, which is area of cross section, as you can see there. We have V, that is potential difference of battery, right, or potential difference across the conductor. Then we have E, that is electric field inside the conductor. This is field inside conductor, right? Then we have I, which is current. Then we have J, which is current density. Then we have what? Rho, which is resistivity or specific resistance. We have sigma, that is conductivity, right? So this meeting will end very soon. So just uh, we'll derive this relation that is between VD and current in the next session. So that will start in another 2 minutes. So just a 2 or 3 minutes maximum break, then we'll derive this relation between drift velocity and current.